Welcome everybody to our weekly O-REU seminar series. Today it's my pleasure to introduce Dr. Bob Hackenberg, who is a staff member at Los Alamos National Laboratory. Bob got his Bachelor of Science in Material Science and Engineering at the University of Pittsburgh, and then his PhD from the University of Virginia in 2001. After that, he went directly to Los Alamos, where he has been working ever since. And I have been very fortunate to interact with Bob while I was at Los Alamos for about 3 years. Bob's self-described interests include everything lamellar, so basically anything that has the shape of layers. And I also have a keen interest in everything that has the shape of layers. So Bob lists out here perlite, bainite, precipitation, cellular, and spinodal microstructures. Not all of those are necessarily layered, but I think that all of them are sort of multi-phase complex composite structures. So there's a lot of interest between us on those two topics. So today, Bob will be giving us a presentation on microstructure, 150 years of ongoing discovery and our attempts to predict and manipulate it in metals and alloys. Bob, take it away.
Okay, thank you very much, Mike, for the introduction, and let's get started. So today, I would like to, let's see if I can advance the slides. Okay, so first, I'd like to acknowledge a few people. First is my summer team, students here, Elaine Moe, who is an REU, who is working on some data mining efforts for very sparse data in the world of precipitation. And on the right side, Jessica Lopez, who I've worked with at LANL for about 2 years, and she's also going to grad school at a different SEC football conference school, and she's doing material science. So we're all working together trying to understand aging. And certainly I'd like to acknowledge National Science Foundation for sponsoring this program, and also a local Los Alamos program that funds this type of work. So thank you. And since I'm talking to a lot of students today, I'd like to mention some of the mentors that I've had along the way and acknowledge them. The first of these is Bill Sofa, who taught a number of courses when I was at the University of Pittsburgh as an undergraduate. He really was a good mentor and helped direct me towards graduate school, towards certain advisors that I looked into. He also hooked me up with my second REU internship between my junior and senior years at Carnegie Mellon under a more of a theorist named Bill Johnson, who does a lot of elastic modeling, and I learned a lot from Bill that summer. And then finally, my PhD advisor, Gary Shiflett, who I spent probably the most time with, obviously being in graduate school. And all three of these really had a really big influence on me. They all taught well. They cared about the details. You had to be a good scientist or want to aspire to be a good scientist. They didn't tolerate sloppy work or the first answer you gave them, right? They always wanted to check and make sure we were really answering the right questions and in the right way. But relevant to this talk is that they knew the history of their discipline. They knew a lot of the characters or heard stories first or second hand and passed a lot of them on to me. And all of them really embrace their vocation as a scientist, as an intellectual adventure, which continues your entire life. And I hope a lot of you doing research for the first time this summer have that experience as well, the first steps of the intellectual adventure, that what you learn in the textbook isn't necessarily true. When you're pushing at the frontiers of research, you're always asking why. And I've asked that about the world of microstructures since I first encountered them way back almost 30 years ago. So if I were to encapsulate this talk in 2 words, it's that microstructure matters, and a little more elaboration. It matters because these microstructures, even though we don't see it, and it's really hard to see, in fact, they hold up the structures of civilized living, large-scale structures, big things, big buildings, big ships, airplanes, go to the moon, stuff like that. It allows us to advance further in the material sense of civilization. Of course, there's much more to civilization than just that, but it's not unimportant. So let's walk through the history of various materials to put this in context. From time immemorial, we've had the Stone Age, and these are materials that are available naturally: rock, clay, and wood. These are great the first two are great in compression, less so in tension. Wood's certainly a very versatile material. We still make houses out of them today because it's very easy to work with. a huge change came about, I'm trying to get the year, 3000 BC-ish time frame, where now metals, and especially ductile metals, became part of the scene. And that's where this is the age of bronze, copper, zinc, and other alloy elements, where you can now shape materials and use and allow them to hold strength and tension and beat them up, and they still stay together, at least for a little while. The big pivot point was the Iron Age, and then really this is a very slow-moving revolution, started at 1500 BC in Turkey and in the Near East region of the world, and it very gradually developed, increasing throughputs until it really took off during the Industrial Revolution. Iron-carbon system has much higher attainable strengths than the copper alloys, which was the next best thing available. And this allows to build really big structures, to span rivers with double-decker bridges like this. This isn't a terribly long bridge, it's here in Pittsburgh, but it certainly gives an indication of what's possible. In the last 100 years, we've entered the aerospace age, where brute force strength is not enough. We also want lightweight, and we want high temperature. So lightweight, we're thinking of lower density, aluminum 2.7, magnesium, I forget, something like 1.9 grams per cc, much lower than the 8 or 9 for copper and iron. Likewise, high temperatures, you use nickel and titanium base alloys. Nickels were really remarkable. You can use it at up to 80% of its melting point. And most things turn to butter, and there's no way you would use it at those temperatures. But nickel is pretty remarkable in other alloys, which we call the super alloys. And so these two regions are what I'm going to talk mostly about today. Finally, we can argue we've been in the plastics age since the 1920s and 30s. Plastics are very important, and certainly the silicon age with the age of computers and integrated circuits. So before I move on, I wanted to just put all these materials in perspective on two axes here. This is done by Mike Ashby from Cambridge. I encourage you to look up his book, Materials, or some of his papers where he plots these things. And notice, first thing to notice, these are logarithmic scales. You have density on the x-axis and strength, yield strength, or ultimate tensile strength, I'm not sure which, on the y-axis. And notice these are logarithmic scales, so these are vast changes in the properties. What's really interesting when you look at the woods, some of the natural materials, they actually have a very variable density and also variable strength. A lot of it is because nature builds in a lot of porosity into the materials to give them a lot of stiffness without a lot of weight. And even today, we're still learning from nature. But if we look at if we really want the higher strength to build skyscrapers and things like that, we need to get to metals and to some extent ceramics. What's interesting about metals, if you look here at steels, cast iron, zinc alloys, titanium, here again the lower density of 4.5, and aluminum alloys down here at about 2 or 3, and magnesium. They all have very narrow bands in the density, and density is what we call thermophysical property or a structure insensitive property. It doesn't really vary a whole lot depending on how you alloy it or heat treat it within certain limits. So you see these are really relatively narrow bounds here. And if we care about strength to weight, there's not a whole lot of scope to change the density, the weight part of it, but you can certainly change the strength. And this is where the world of microstructure comes in. You see these bands here going up almost an order of magnitude for steel, and likewise for all the other alloy systems. You get factors of 2, 3, 4 difference between the pure metal and the alloyed metal when it's appropriately heat treated. I'm not going to spend any more time on this plot, but I would certainly encourage you to return to this and take a hard look at it and ask questions about why do we get certain properties? Why can't I go even higher? What is the theoretical limit for this? That's a great question for further study. So what's inside my talk today? I'm going to focus mainly on metallic structural alloys, and I'll define what they are. If I have time, maybe during Q&A, I'll contrast material science versus materials engineering. These are not one and the same thing. Just be aware of that. A lot of you are doing the science, and that's very academic focused, but the engineering is the customer ultimately paying for your job down the road for a lot of you. I'm going to ignore most of the other parts of that Ashby plot, including concrete, which is by tonnage by far the biggest user of materials, very, very important material. That's also the domain of civil engineering. And as much as it breaks my heart, I'm not going to talk a whole lot about phase diagrams, diffusion, which are really important to the story. So as a preview of my take-home messages, the first is that microstructure matters, and we've only learned about this in the last 150 years or so, starting in 1863, and it was a very herky-jerky motion towards understanding. The second take-home message, and I heard this from John Kahn along 20-some years ago at a conference. You know, he said he got his degree. He's a famous theorist, by the way. And he said he got his degree in chemistry, and he realized that chemistry was a relatively mature science. And he had the option of either continuing in chemistry or going into this physical metallurgy, working at General Electric. And he chose to go into physical metallurgy, or what we call material science. And he realized it was still a very young discipline. It's a bit of a wild west. We're still discovering a lot of stuff. And a lot of our ideas in the textbooks, even today, could well be wrong, or at a minimum, incomplete. And it's up to you. I'm looking to all these students to use your imagination and curiosity, not just your analytical chops, which all of you are really good at and you're getting better at it, but to use your imagination to envision other ways of looking at materials. So that's one of my take-home messages. So I'm going to talk about the origins of material science, define structural materials, talk about the age of discovery, focus on crystals, defects, and precipitates, which really define microstructure, at least part of it. I can't cover everything in this talk, but those are three I'm going to focus on. Talk a little bit about materials engineering, how we optimize microstructures for structural materials. Talk about hierarchy of microstructure length scales, materials considered as a system, and some concluding thoughts. So firstly, origins of material science. And so where did MSc originate, material science and engineering? There's three strands which didn't really talk to each other for a long time. The first is the tradition of science, which goes way back, and it started with the pre-scientific era of alchemy, where a lot of philosophy was thrown in and not necessarily very helpful. Chemistry gradually evolved in the 1700s, and physics joined the party around 1900 when crystallography came into being, and now the physicist tools could be applied to a lot of materials problems. Independent of that, largely independent of that, was the tradition of engineering, and this goes back thousands of years. Regardless of whether you know enough science, you can do empirical studies and just keep building things bigger and better. And these are two examples from early industrial revolution era England, southwest England near Cornwall, which is very famous for the mines where they extracted copper and tin, which is your brass, even back to Roman times. And really the age of steam really created this virtuous cycle where you're putting materials to greater demands, but at the same time things like the steam engine can allow you to extract ore bodies at greater and greater depths and apply greater energy to extracting materials, turning them from oxide to metal, purifying them, doing things like that. So that's the middle strand. And then on the far right, we have the tradition of craft. This is work of artisans, and you're usually working for the king, the prince, the aristocrat, or the tyrant, or the general, whoever has the money or the power at the time. And these arts, they capture a lot of implicit knowledge. They can't really write it down as science, and you wouldn't really call this plate engineering, but certainly a huge amount of craftsmanship went into these things. They're really objects of beauty. So I'm going to talk a fair amount about iron because it really is the classic structural material. If we consider the 7 metals of antiquity of gold, silver, mercury, copper, iron, tin, and lead, of these, iron far surpassed the others in terms of its raw strength, with copper being the number 2 on this list. And even today it remains the go-to structural material. If you're not sure what you want, you probably want steel, because it has 3 things going for it, which is still true today. It's strong, it's ductile, and it's cheap. And this combination is really hard to beat. And oh, by the way, it's formable and it's weldable, which is important for more modern applications like forming auto bodies and larger scale structures that you weld together instead of rivet, a much more efficient process. Making iron is straightforward. There's lots of it in the ground, certainly concentrated some places more than others. You can reduce the iron oxide to iron metal in an air furnace. You basically use the oxygen and the air we breathe, and you just got to heat it up. And you don't need chemicals, vacuum, or electricity. These are all late 19th, early 20th century inventions, which were not available to the ancients. So we were making steel for thousands of years, but it's a very, very small scale. until recently. So what is a structural material? Because that's where microstructure really matters the most in terms of modifying the microstructure in our favor. It's any material where mechanical strength is crucial. And I will caveat this that tensile loading is important, and this is what separates metals from ceramics. Ceramics generally are not good at tensile loading. They're very strong and generally quite brittle. So you always want some ductility, though mechanical engineers don't necessarily rely on it, but it's a part of the factor of safety, as it were. It supports many times its own weight, and these could be static loads, whether holding up skyscrapers or holding gas pressures and pipelines, and likewise dynamic loads up to thousands of G-forces. This is the world of jet engines, gas turbines, things are spinning thousands of RPM. There's a lot of G-forces there. And likewise, those of you in creds especially, you see impact loading, blast shockwaves. These are like single-use objects where you only have to survive once, and that's good enough, as opposed to millions of cycles of rotation, whether it's an automobile engine or a jet engine. So once we were able to get structural materials able to hold many times their own weight, that opened up possibilities for the built landscape. So we finally moved beyond the age of stone and wood, which can only give you a certain height. This is some ruins from 400 years ago here in New Mexico. And even with the best of masonry, you can only build a building about 10, 12 stories before the foundation has to be widened so much that it becomes impractical. Nowadays, we build skyscrapers. Here's the iconic PPG place in Pittsburgh. And I assure you, this is not held up by the glass that you see, as beautiful as it is. I was a kid growing up when this building was put up in the 1980s, and it is a steel skeleton underneath all this. But that steel skeleton allows us to play tricks, to do things like this, to have glass facades, as an example. So I should mention mechanical strength is necessary, but it's not enough. The material has to survive its environment, and salt water is a particularly nasty. The chloride ion is particularly nasty to a lot of metals, especially steel, as is high temperature, radiation, and chemical exposure. All these things, and perhaps in combination, combine to weaken metals and turn it back to the state of nature, which is oxide, which is not what we want. We went through a lot of effort to make it metal, and nature wants to turn it back to oxide. So we have to play tricks to either deliberately alloying it or adding surface coatings or things like sacrificial anodes to protect structures sitting in the Gulf of Mexico, for example. As an aside, corrosion in design studies is rarely considered up front, or at least given the diligence it really deserves. However, once it starts happening, I say repent at leisure, tongue-in-cheek, because it's often a crisis situation when things start corroding, because no one was really planning for it or expecting it, and things are going south fast. So if there are some of you that are working on corrosion and others may be considering it, it is a great field. It is very complex. I don't know a whole lot about corrosion, perhaps enough to be dangerous, but something to really consider. There's always a need for corrosion. Rust is not going away anytime soon. So there's two paradigms of materials design, and which changed with the microstructure revolution in the last 150 years. And on the left side is what I call the good enough, or this is as good as I can give you, customer, whether it's armor or military hardware, cannons, whatever it is. They were unable to improve materials on a time scale that the customer cares about. And if you ever work with customers, they're always impatient. They want your product yesterday. They can't wait years or decades or centuries for things to very slowly improve through things like trial and error. Nowadays, we expect materials to work and work really well. This is an example of a highly engineered structure where it requires very high strengths of your steel cable, pulling this cable car up a mile above the city of Albuquerque. And this cabin here is made of relatively lightweight metals, probably aluminum, if I were to guess, because you want to maximize the payload, the paying customers inside, and minimize the weight of your structure. So the more you can minimize the weight, the better it is. At the same time, you don't want this to fall down after it goes up and down the first 10 times. You want to have it so you can predict failure in a controlled way and replace the cables and things like that well before there's a real problem, because you don't want people to get killed or in accidents and things like that because of our ignorance. So in fact, it was our ignorance that really, and pushing the hard demanding applications which caused problems, which prompted the microstructure revolution. So by 1860, the output of steel really improved, vastly improved through two industrial processes, the Bessemer and the Siemens-Martin process for making steel. This can make steel in 20 minutes. This can make a lot of steel in about 9 hours, much different time scale, but both of these are orders of magnitude greater than the blacksmith crucible methods, for example. So we were making large things, battleships and the like, skyscrapers. And by 1880, the good enough was no longer adequate. We were suffering catastrophic failures seemingly randomly. And one example here is a railroad bridge over in Scotland, crossing a relatively wide span of water, not very deep, but certainly a long span. And during a winter storm in 1879, as the train was crossing the topmost part of this bridge that you see here, is in the middle of a windstorm, and the whole thing collapsed, including the train, and about 100 people died in that. And the uproar, from that, the public outcry, so why does this happen? And there are all sorts of things were to blame for this, including poor design for wind loading, but they also didn't spare the materials. They started to ask hard questions. What makes a good steel or a bad steel? Is the steel good or bad? And even today you see TV shows about the Titanic and why did it sink, and there are always theories that maybe it was really bad steel. Turns out the steel for Titanic wasn't that bad. It was pretty good for the day, but that doesn't mean it's always necessarily innocent. So the materials always get blamed when there's an accident. So luckily, the first tools needed to encounter microstructure were emerging at the same time, and we're going to talk about that after our first pi over 4 minute break, and I'll to rest your brain or to look at some of these sayings.
Well,
okay,
sorry, go ahead.
Go ahead.
No, I was just going to say that while this pi over 4 minute break is going on, I thought I would interject two of my own big picture sort of things that I've learned as a result of working in material science. But maybe I should leave that for later.
Yeah, why don't we leave that till later to keep rolling here. Is there another question?
Can you hear me?
Barely. Speak up.
Hey, who was the quote for the 3 types of crystal structures? Who said that?
I
like it.
I remembered it a while ago, but I've been reading so many papers in the last week, I forgot. If I find out, I will tell you. But I think it's one of these things where it's been repeated so many times, the originator is really hard to come by. But yeah, if you do ceramics and if you do low symmetry materials, minerals, you're going to laugh, or you're a crystallographer, because everything's monoclinic in the world of a lot of minerals, for example. Monoclinic is just, it's crazy. Okay, let's go ahead and move on to discovery of microstructure. So I'm going to skip over this, but the bottom line is there's a lot of ideas from chemistry and which were not very helpful. Chemistry had its revolution in around the year 1800, and so people said, we finally understand the world of molecules, so certainly metals and alloys are also molecular or amorphous. A lot of people thought a good metal was amorphous, a bad metal was crystalline. That's not true. So as I mentioned before, the age of steam, whether it's railroads, I showed a few pictures here, or things like the riverboats on the Mississippi, those boilers were exposed to pretty aggressive conditions, right? Not the best water, had some impurities, though certainly not salt water, thank goodness. High temperatures and fatigue. And sooner or later, the thing was going to blow, and they did blow every now and then, and people died, the boat sank, and just catastrophic explosions of these wooden boats. And that's really what led to the development of institutions like ASME, the Mechanical Engineer Society, and standards for pressure vessels and things like that. So same thing with railroads. We kept pushing things longer, harder, carry bigger loads, and eventually stuff is going to break. So a lot of the early efforts were focused on phase transformations in steel, and the good news is these phase transformations are easy to find, quote unquote, and that's largely because you have an allotropic phase change in pure iron, which also extends into the steel range of SCC to BCC, and essentially 100% of the microstructure changes at around 700, 800 Celsius as you quench or slowly cool the material. And this was relatively easy to see, certainly by strength if you do hardness or tensile, and certainly by other indirect methods like resistivity, ferromagnetism, and density. So it's broadcasting on all channels, and people were observing this, and everyone wants to know what makes steel so hard. And as Cyril Stanley Smith, the great historian of metallurgy, remarked, the paradox is that one of the most complex materials to understand, that is steel, was studied first. Understanding martensite was that's not where you would start knowing what you know today. Martensite's actually especially ferrous martensite is actually quite complex. But that's I think Raimondo has a phrase, if funding focuses minds or something like that, focuses efforts. So certainly the people who cared, the captains of industry, cared about steel. So light optical microscopy was kind of slow to come to metallurgy, partly because it started in the 1600s with the transmitted light microscope. And if you're looking at minerals or biological specimens, that's fine. But if you're looking at metals and alloys, the first thing they look at in all these failures is the fracture surface. And I won't say it's bad to look at the fracture surface, but it gives you a very incomplete knowledge of what's going on, because there could be corrosion, overheating, wear going on. The root causes, especially for things like fatigue, they're often miles away, literally, metaphorically. Could be millimeters away from the final fracture surface. Actually doing failure investigations, finding root causes is incredibly hard. I was involved in one at Los Alamos last year, and boy, the arguments we had amongst the team, we had 8 of us, we were trying to sort this out, tasked to sort out a steel failure, and it was really hard. There's a lot of plausible but not provable things. So this is the world that they faced as well, as things kept breaking. So the pioneer in metallography, as we know today, is Henry Clifton Sorby. He was a gentleman scientist, and he didn't have to write proposals or do any of the stuff that all your professors have to do today to keep their research groups going and funded and paying students, not the least of which. He was very proficient with transmitted light optical microscopy. So again, geology studies where things are translucent, some crystals. He adapted this microscope. This is the big change for reflected light microscopy, which now can be applied to opaque materials such as iron and steel and other metals. This is probably the first metallograph image taken of some Swedish wrought iron in July of 1863, and he noticed this structure called Vimenstatten, which actually harkened back 50 years to a famous picture of a meteorite taken at pretty much 1x or 4x magnification. Of course, the meteorite has the advantage of cooling 1 degree per million years kind of thing, so the structures are incredibly coarse. This was 15x. This is actually rather coarse itself, but he didn't really know how to interpret it, and this is a premature discovery. And he had other interests. He had a little yacht he would go around and do botanical researches and things like that. However, he did return to it as others got interested in the mid-1880s. And that's where he published his famous papers on pearlite, which Mike was alluding to. I have a soft spot for anything lamellar, and he really accurately described pearlite. So systematic studies, including metallography, began in the 1880s. Here, 2 gentlemen from France and from Germany, Martens, who from Martensite is named, and their toolkit was threefold: chemical analysis. You're really flying blind if you don't know the composition of your steel or your alloy. And for a long time, people didn't know the composition until chemical methods came online. So that was good. They didn't apply this newly developed metallography with the light optical microscope, which replaced fractography. So they're looking at the bulk structure, hopefully a representative structure after controlled heat treatments, which they can now control better, or at least measure, once the thermocouple was invented. Instead of just eyeballing the temperature as a red heat or a yellow heat in a furnace, that had limitations. Now we can precisely measure phase transformations. So what's interesting is the first microstructure raised more questions than they answered, which isn't that surprising. The question is, why is steel so hard? That's what really focused minds. And there are 2 camps. The allotropists held that there's a diamond hard allotrope retained on quenching. Beta iron, I encourage you to look that up on your phase diagram book. Tell me if you find it. And in the other camp was the carbonists, and they thought in terms of chemistry, of molecular or colloidal arrangements of iron and carbon, somehow altered on quenching, and if you quench, you get this compound with the chemical formula Fe24C called hardenite, and if you slow cool, you get this structure which we now know as perlite, and if you cool it really slowly, you can see these lamellae resolved by light optical microscopy. But there's a controversy between these two camps and others sitting on the sidelines or not quite sure who to believe. There's a 100-page debate in AIME 1898 that I read through. It was really fun to read, because you're seeing people trying to see different elements of the truth and trying to grasp it, but not quite getting the whole picture. And you want to just yell at them and say, don't you understand that carbon is arranged in such and such a way? So more confusion, what is trustite? I encourage also to look this up. Do you find this in your textbooks today? Probably not. And part of the reason is they named things without understanding the internal structure. Nowadays, I look at this and I see a prior austenite grain boundary. Here's your austenite grain, and here's a bunch of perlite nodules growing out. But the problem is you can't see the lamellae inside the perlite. Compare that with this previous picture from Arnold. This is a much slower cooled perlite where you can see it by light optical. But for a lot of perlites, you simply can't resolve the lamellae. So people argued, and this is just a list of definitions when they did a poll back in 1912, and you see there's all sorts of theories, and none of them are particularly useful. And so we would have been stuck there for a very long time until X-ray diffraction broke the logjam. So once X-rays were discovered in 1912, and by the 1920s we were applying them to metals, and they were revealed to be overwhelmingly crystalline with a small fraction of defects, and they're packed as atoms, not molecules. And this is where physics entered the equation, because now crystallography and force constants, interatomic potentials, things like that came into play. So crystals are all well and good, but this whole thing about defects really drove people nuts. Here's Sir Charles Frank. He was one of the founders of dislocation theory, worked in Bristol in the 1930s and 40s along with Nabarro and Sir Neville Mott. Crystals are like people. It's the defects that make them interesting. Same thing holds for materials. So I would argue dislocations are the keystone to understanding structural materials. And the big question which drove people mad is that real crystals are 1,000 times weaker than what was expected. A physicist can calculate with an interatomic potential theoretical strength of a crystal, and it's roughly the elastic modulus divided by 10. If you ever looked up the modulus, that is a really big number. Even divided by 10, it's still a really big number. And yet, you do a tensile test, and materials fail at far lower stresses. You can't just hand wave away that kind of discrepancy. There's something else going on. And it turns out theorists came up with the answer before the experimentalists were able to catch up. In the 1930s, this idea of the dislocation was postulated theoretically by 3 different workers, and the characteristic edge and screw dislocation, and this is what made a big change. Now the shear stress needed to plastically deform a material could be explained by just breaking the bonds here locally at one dislocation. And you may have a train of dislocations separated by a certain amount, as you see in this TEM image. But it wasn't until the 50s we actually saw these by TEM. It wasn't until the 70s and 80s we saw it by atomic resolution transmission electron microscopy, which really shows very nice proof of edge dislocations. So I mentioned physics entered the equation. Chemistry kind of got separated because we're not dealing with amorphous and molecules, but physics also really struggled because a real material is a perfect lattice plus defects. So describing one defect is fine for physics, but describing millions of them when you undergo work hardening where you have dislocation, multiplication, and they're tangling during work hardening and other processes, you have highly nonlinear interactions, and you just can't write a differential equation to solve all that all at once. At best, you can do numerical models, which people are doing today, but even still, the computers struggle to keep up. The computers don't have the horsepower still to do really large-scale simulations. So the defects control the properties and they limit the performance. This is why microstructure matters. So when we engineer strong materials, there's two approaches. One is to remove the defects entirely, and apart from a few cases like metal whiskers, we don't go down that route. Nature served us lemons and we're making lemonade, so we strengthen already imperfect crystals by adding even more imperfections to resist dislocation motion. In particular, we add second phases and we add grain boundaries. We essentially refine the grain size. And as an example, these are some aluminum 2 copper compound theta prime precipitates, and the white area is the FCC matrix they sit in. So this is about 5% precipitates. This is what holds up your airplanes, the aluminum alloys in airplanes. Having these, and the really important thing is to have these homogeneously dispersed, because the dislocations will find a weak point. If there's any weak point where there's a really big gap between the nearest cluster of precipitates, it'll just blow through there, and that's where dislocations will pile up, you get an incipient crack, and then things fail. So you really want to homogeneously distribute it. And that's actually not necessarily easy to get. But we learned a trick, and it came about through studies of age hardening. So this is the age of aerospace. There's work going on in Berlin, working on the Zeppelins and early model aircraft, discovered by Wilm, the phenomena of age hardening in aluminum copper. However, compared to steel, it's much harder to observe. You only have a few percent of the microstructure which changes, those few percent precipitates. Furthermore, you really can't see this by light optical. Nanometer scale clusters and precipitates give you the optimum strengthening. By the time you can see the precipitates, it's generally overaged and over the hill and not very useful. So the scientific understanding of this came about by the application of X-rays about a decade later by some workers at National Bureau of Standards, now known as NIST, in Washington, D.C., and they discovered by X-ray diffraction and the phase diagram basis. And after this principle was discovered, formerly weak elements were made strong, and at least 15 elements were precipitation hardened scientifically within a decade. So now alloy development can go much faster. You don't have to wait centuries of trial and error going on. And in fact, I've asked Elaine Moe to look at how much of the periodic table has actually been age hardened. And I'm asking her to look for really odd systems that aren't least famous 15, for example. And that's really her challenge this summer. So the principle that Merica, Waltenberg, and Scott discovered was the phase diagram principle, decreasing solid solubility of decreasing temperatures. So here's aluminum copper, temperatures up here. Here's your melting point of 660 or 640 for aluminum. Here's your composition axis. Generally, you want to pack in as much as you can, other things being equal, because you get more precipitates if you have more solute. So you don't want to cool straight from liquid, because remember, you get coring and segregation, and you get inhomogeneous microstructures. They are the enemy. You want very homogeneous microstructures. So you solutionize, you may have homogenized it. So the important thing is solutionizing in the single phase region. You water quench, or quench by some means, to trap all those copper atoms in solution, and then you reheat. So that's shown here. So you're solutionizing, here's your temperature axis, you're solutionizing, you're quenching, avoiding the hardening curve on the way down, and then you either let it sit through natural aging, or you speed it up by artificial aging, say at 100, 200 Celsius for the case of aluminum. So once you understand this principle, and you apply the phase diagrams, which at the same time are being developed. They were essentially invented around 1900. Once people realized the Gibbs phase rule and the other principles of phase diagram construction, experimental work took off and hasn't really let up ever since, at least for binaries and ternaries. So in practice, the age hardening sequence that you get, so here's hardness versus time, and I should mention time is on a log scale. Precipitate radius is more of a linear scale. And in general, as the precipitates grow larger, they nucleate and grow, and they grow larger and larger, they present a bigger obstacle to dislocations, because the dislocation has to cut through a bigger and bigger particle as time goes on, and that's why your hardness goes up. It simply resists dislocation activity. However, this ought to keep going up forever, except other things intervene, such as coarsening. And as the precipitates coarsen, they get further apart. Their spacing now gets further apart, so it's more energetically favorable for that dislocation to bow between the precipitates instead of cutting through them. And as it bows through, it creates a loop. So this is called O-REU looping. And you can get continuous coarsening, or you can get abrupt coarsening through what's called cellular precipitation. This is one of the pictures I took in one of my early works. And this is not a microstructure, which is really good because you go from here to here really fast. So now you've really dropped the properties. So I don't have time to go through the rest of the techniques, but I'll just kind of go through quickly in a chart showing the evolution. We started with light optical, came online in the 1880s, X-ray in 1920s, electron microscopy. Now we can see much more directly the precipitates and the defects in the 50s. This is the world that I worked in for a long time as a researcher in front of an electron microscope, and certainly making specimens was a real pain and a trial experience. Electron microprobe, atom probe, now these allow not just crystallography, but also the chemistry on very local scales. You're not just stuck with doing a chemical analysis of a 1 gram sample, which has, how many millions of atoms, 10 to the 22 atoms in that. Now you can sample thousands or millions of atoms, which are very localized and where the inhomogeneities in the microstructure and the phase transformations action is happening. By the 70s, we had EDS and atomic resolution microscopy, and more recently, electron backscatter has become very popular, along with 3D methods, including the focused ion beam, which you can slice and dice much faster. So we will take a quick break before moving to the last part of the talk. Okay, so let's go ahead and move on and talk a little bit about materials engineering. I'm just going to give a few examples of processing techniques we've used to optimize microstructure. The first of these is modifying some of the time temperature cycles for age hardening. So we talked last time earlier about the nominal quench and then artificial aging or natural aging. One trick we can play on artificial aging is to actually do it at 2 different temperatures. The first is to maximize the nucleation density, or the density of the particles, to get them as finely spaced as possible. You'd rather have many very fine particles than a few coarse particles. So if you can start the nucleation process and then accelerate the growth stage at the second stage, that gives you a big advantage. Another thing in increasing homogeneity is to give it a stretch. Give your aluminum sheet, for example, this is used in aluminum, 5% stretch. That adds just enough dislocations and dislocation tangles that it's really good for making sure particles nucleate everywhere, and especially avoiding things like grain boundary precipitation, which is it's localized and not necessarily very good. Another trick is to refrigerate the material because it is age hardening if it's a low melter like aluminum or possibly magnesium. So you want to do your forming process while the material is weak, so you need less forming stresses, and then you can finally do the aging. You want to harden the material at the very end, not at the beginning. Another game we've been playing for a long time, at least in steels, at least 50 years in steels, and more recently for all these bunch of other materials, is grain refinement. Generally, as cast structures, which is how most materials start life, they are really coarse. Their length scales are 10, maybe 100 microns, and that's just miles apart in terms of age hardening precipitation features. So if you can refine those grains, you can do a lot. So we raise our dislocation and our interface density by traditional heat it and beat it, and by doing it in an intelligent way, so where you're doing it right near the recrystallization temperature. For example, in steel processing, there are more recent techniques such as severe plastic deformation, like high pressure torsion or equal channel angular extrusion, which really put a ton of cold work into the material. Wire making's been around for a while. This plot here, this is a really big scale. 1,000 MPa actually are pretty respectable for just a garden variety steel of tensile strength. But if you just keep pulling it to strains of 2, 3, even 4 true strain, you can get a huge change in the structure. I mean, the wires really hold up a lot of things, not just suspension bridges. Yeah, I should mention, this is perlite here. It's a natural composite. There's not much element or alloy content here. This is a fantastic material. It's really an unsung hero of a lot of our structural materials. It's also holding up the tires in your car, by the way, steel belted radials. The second trick related to this is getting beyond the ductility-strength trade-off. So if we hold fixed an alloy composition and the grain size for at least the last 100 years, we've known you can go up and down this ductility strength, what I call the banana plot, through cold work or precipitation, and generally you're going to get one or the other. You get high ductility and low strength, like right here, or high strength, low ductility, or some compromised property in here. However, in the late 40s, early 50s, we discovered that by varying the grain size, you get two for the price of one. So going from coarse grain to fine grain moves this banana plot up and to the right, which is exactly what you want. It's almost too good to be true. This is especially true for steels, where they undergo ductile brittle transition temperature. DBTT is the Achilles heel of body center cubic materials, especially for steels. So if you can push this to a lower, more favorable range, that's wonderful. At the same time, the Hall-Petz relationship increases your ductility, where you have your yield strength is equal to summation of all the other contributors, sigma naught plus K, some constant divided by your grain diameter. So as this grain diameter gets smaller, your strength goes up, other things being equal. So we've been playing this game for a long time in steels. More recently, the promise of nanomaterials was partly premised on pushing this Hall-Petz to its uttermost limits. I don't have a whole lot of time to talk about this chart comparing material science versus engineering, but if you want to return to it in a discussion, we can. There are some philosophical differences. And finally, I get to the money slide here of materials as a system in terms of the hierarchy. This is stuff below the naked eye. You need various microscopy techniques to manage all these length scales from macro scale down to the micro scale. The region we deal with is the micron plus or minus a few orders of magnitude. This is the area where the crystals modified by those defects, such as dislocations, vacancies, dispersoids, and where they interact and ultimately cause cracks and macro scale cracks, which you can see or detect by non-destructive assay. This is where all the action is taking place. And there's various techniques. I was mentioning, the as-cast structure. This is really coarse. This is half a millimeter. This is 500 micron bars. So these dislocations could blow through the weak part and never really get strengthened by the strong part. Now, as-cast is good enough for a lot of applications, and it's favorable because of economics, because rot processing, you pay a lot more for that, but you get a lot more for it as well. So we have all these techniques which are helping feed the modeling efforts and theory efforts, but linking these length scales is the grand challenge, and we still struggle with that today. I'd say we've come some ways, but I still think because of the nonlinear interactions and just computational horsepower, we're simply not there. So these are the structure-sensitive properties: yield strength, fracture toughness, fatigue, which really are the underpinnings of structural materials. So a few concluding thoughts. Microstructure matters. I hope gave you some sense of that. Where do we stand after first century? Material science is still young. Well, I would say we're still struggling with complexity. Maybe not drowning, but struggling. There's a lot of variables. Hysteresis, the path dependency of microstructure. You can't reverse the order of the steps in a recipe when you're cooking without, dire results for your food product. Same thing is true about microstructure. The path dependency matters. The vast number of potential phase diagrams or permutations. Just ask Elaine, my student. She is looking at permutations of just binary elements, pairs on the phase diagram. Huge number. It's a factorial problem. And again, the nonlinear interactions. So where do we go from here? I have three messages for experimentalists, modelers, and theorists, and then we'll be done. For experimentalists, can you please speed up measurements? Measurements are very painstaking, slow. Can you make it high throughput? I thought about this a lot. I'm an experimentalist, used to toil away in the lab. Can we spend time replicating experiments? We spend time discovering new stuff, but rarely replicating other people's work or our own work. You always get two different results, and then you always ask why. They may differ by a lot or a little. It's a learning experience. Interfacial energy is a huge lever arm in the nucleation equation. We do not know these in the solid state well at all. It's very hard to measure. And finally, for experimentalists, can you design a perfect experiment to be the fly on the wall as a nucleation event happens, as a phase transformation interface passes by, say pearlite or bainite, a radiation damage cascade unfolds, or a loading event such as shock loading. You want to be standing there in the ocean as the swell comes in and you feel the push and pull of those atoms, the interatomic forces. Can you design that in situ experiment where you feel that push and pull of those restless rhythms of the atoms as they change from one phase or one state to another? For you modelers, linking phenomena across length scales, I talked about that. Can you do this rapidly for real-time process control? This is a big selling point for additive manufacturing. If you can measure stuff, you can actually change it on the fly. I'm sure some of you may be working on that. And I'll just skip to the bottom here. Data scientists, can you develop, can you efficiently collect, organize, and visualize the very sparse, heterogeneous structure-aware data? Again, the number of permutations is huge, but the data, when you look at the hyperdimensional space of structure, composition, processing, it is gigantic, and it's really sparsely populated. And I would say machine learning has its role, but don't just stop there. Don't just trust what the machine tells you, because it's only as good as the data that goes in. And because the data is sparse, you really need to have a human in the loop. And I really plead to help the human expert with better visualization and simpler ways of extracting data out of papers. Something that simple is actually quite hard and out of figures. And then finally, theory. There's tons of modeling going on today, but not much theory. Theory and you theorists, we need you. And in my particular world, I want to know, what is the Newton's law equivalent for the kinetics of microstructure development? Yes, we use some equations like phase field, which may get us to a certain distance, but I'm not sure if they're the final answer. And all these folks here on this slide thought about these kind of problems. I was really lucky to meet both John Kahn and Matt Hillard at various conferences over the years. Clarence Zener certainly was an inspiration. I never met him, but I should mention he was 8 institutions, including Texas A&M, for a while, I believe, in the 1960s. He did a lot of work. So this is a golden age of theory, of 50s and 60s. I don't see a whole lot of theory today. Part of it is you can't fund it easily. You can't premise it on expected results. Theory, there's a eureka moment, you know. A lot of nothing happens for years, and then he yells eureka, you know. And we need these people. So I get to the end here, and I'll just leave you with this and take any questions. Thank you.